Greetings to all. In the last lecture, we have seen the 5 basic terms of probability, and we have defined an event as a subset of sample space. In this lecture, we will see the relationship among the events and then define the probability of an event and then some of the probability axioms and extend up to Bayes theorem concepts. An event is defined to be a subset of a sample space. And also we have seen that by probability, we always mean probability of an event. So let us see some of the relationships among various events. When an event is said to be equally likely events, that is, events that have the same theoretical probability or the events that have the same likelihood of occurring are said to be equally likely events. Consider the experiment of tossing a coin. The outcomes are head and tail. The event of getting a head and the event of getting a tail are equally likely. In a similar way, when we roll a die, the outcomes are 1, 2, 3, 4, 5, and 6. All the outcomes are equally likely. So, the scenario is if we perform a coin tossing experiment repeatedly using an unbiased coin, and after repeating several trials, one might feel that the head appears more often than tail, whereas another might feel the tail appears more than the head. However, in reality, the occurrence of either outcome has equal probability. That is, the occurrence of either of the two outcomes, head and tail, are equally likely. So, equally likely events are defined as the events which have got equal chances of occurring. Next, let us see what is an exhaustive event. The event such that at least one of the events compulsorily occurs. Then such events are said to be exhaustive events. A set of events which are related to a random experiment is called exhaustive set of events if at least one of the event must necessarily occur. In tossing a coin, the outcome will be head or tail. Any one of the outcome will definitely happen. Such events are called as exhaustive events. Next, what is a disjoint event or mutually exclusive event? The events are called mutually exclusive with respect to an experiment if any two events cannot occur simultaneously. That means there are no common elements between the two corresponding events. That is, the occurrence of one event prevents the occurrence of other event. The same example of tossing a coin, head and tail are mutually exclusive events. That is, if we toss a coin, if head is occurring, tail will not occur. Suppose if tail occurs, head will not occur. So they are disjoint events. The happening of one event will prevent the happening or not happening of the other event. In such cases, they are called mutually exclusive. When two events are said to be independent, that is, occurrence of one event has no influence on the occurrence or non-occurrence of the other event. We'll consider the same example of tossing a coin. Suppose the coin is tossed by two different persons. Person A and B, both of them toss a coin. Getting a head in person A will not affect getting head in the person B. So, these two events have no influence of one getting an event and other not getting an event. Such events are called as independent events. What is a complementary event? If getting a head is an event A, then getting a tail is the complement of that. That is, the event A does not occur. So the complement of any event A is the event not A. It is denoted by A bar. So these are some of the commonly used terms in the probability concepts. Next, let us define what is the probability of an event. The first definition is the relative frequency definition. As the name goes, it is defined with performing an experiment n number of times. So frequency denotes the number of times an experiment is performed. Suppose that a random experiment is repeated n number of times. And if a particular event A occurs n a number of times, then the probability of A is denoted by P of A is defined as the probability of getting an event A is equal to limit n tends to infinity NA divided by N. That is the number of times an event A occurs divided by the total number of times an experiment is performed. And the number of times that experiment performed is infinitely large. So by performing an experiment large number of times, that is several times, and if an event A occurs NA times, then the probability of an event A is denoted by NA by A, that is the limiting value. This relative frequency definition has got certain limitations. That is, whenever this limit does not exist, the probability of an event cannot be studied. Also, there are certain cases where we have to perform an experiment by using some expensive resources or some resources which are very scarce, or there may be some resources which are destructive in nature. In those cases, studying the probability of an event cannot be done by performing the experiment n number of times. So in those cases, probability of that event cannot be calculated by using relative frequency definition. So we go for the classical definition of probability. But this relative frequency definition has got significant engineering value when it can be wisely used. So what is the classical definition of probability? So the classical approach goes with the probability of an event without performing the experiment. Without performing the experiment, we calculate the probability of an event. So this is done by counting the total number of possible outcomes of the experiment and the number of outcomes that are favorable to the occurrence of an event A. So the probability of an event A is given by the number of favorable outcomes divided by the number of total outcomes, where it is assumed that all the outcomes are equally likely. So I repeat the classical definition of probability. Probability of an event A is the number of favorable outcomes divided by the total number of outcomes. So with this classical definition of probability, let us go with some notations that will be used throughout. For any two events A and B, P of A denotes probability of occurrence of the event A. P of A complement or P of A bar, it is also represented sometimes by P of A dashed, which means probability that event A does not occur. That is, probability that event A does not occur means it is the complementary event of A. Next is P of A union B. This is the probability of occurrence of either A or B or both. P of A intersection B, sometimes given by P of A B, which is the probability of joint occurrence of A and B. What is the probability that both events A and B occurs? The next is P of A given B, which is the conditional probability of A with the condition that B has already occurred. So this is read as the conditional probability of A given B. In a similar way, we can define the probability of B with the condition that A has already happened. So this is the conditional probability of B given A. And similarly, A contained in B implies an event A occurring, implying that event B has already occurred. With these notations, let us go for some of the probability axioms. The first axiom is the axiom of positiveness. The probability of any event A always lies between 0 and 1. The least value is 0 and the highest value is 1. And the probability of any event A will always lie between 0 and 1. Next axiom is the probability of an impossible event is 0. That is the probability of a null event, the event which is not possible. So the probability of an impossible event is 0. The next is the probability of a sure event or the probability of a certain event is 1. And this axiom is called as the axiom of certainty. Next is P of A complement is equal to 1 minus P of A. The next is the axiom of addition. That is, for any two events A and B, P of A union B is equal to P of A plus P of B minus P of A intersection B. And in the case of mutually exclusive events, we know that A intersection B is empty. That is, there is no outcome which is common for both A and B. In that case, the probability of A intersection B is equal to probability of phi, which is equal to 0. So for mutually exclusive events, we have P of A union B is equal to P of A plus P of B, where P of A intersection B is equal to 0. The next comes the axiom of multiplication or compound theorem. So what is P of A and B? What is the probability that A and B happens? This can be defined by, suppose say we have P of A and B. If event A happens first, it is equal to P of A into P of B with the condition that A has already happened. Or suppose if event B happens first, then we write it as P of B into P of A with the condition that B has already happened. So from this compound theorem, we can define what is P of B given A. So P of B given A is equal to P of A intersection B divided by P of A, where P of A is not equal to 0. In a similar way, we can define what is the conditional probability of A given B. So P of A given B is equal to P of A intersection B divided by P of B with the condition that P of B is not equal to 0. So from the axiom of multiplication, we can define what is the conditional probability of A given B and the conditional probability of B given A. For events A and B that are statistically independent, P of A intersection B is equal to P of A into P of B. Since the events are independent, where one will not have influence of the other, it is P of A. That is, either A can happen first or B can happen first. So they are statistically independent. Hence, P of A intersection B equal to the product of their individual probabilities. If A is independent of B, P of A given B is equal to P of A. B is independent of A implies P of B given A is equal to P of B. And we see that for A contained in B, P of A is less than or equal to P of B. Now for any two events, we have seen the axioms. Now we can extend our study to infinite number of sets. We call it as infinite additivity and infinite multiplication. That is, for countably infinite sets A1, A2, etc. An of pairwise disjoint events, we have the probability of A1 plus A2, etc. An is equal to the sum of the individual probabilities. So this is called the infinite additivity axiom. For same sets A1, A2, etc. An, for pairwise independent events, we can define the joint occurrence of P of A1, A2, etc. An as product of their individual probabilities. So this is that is the sequence of independent experiments is a way of describing a sequence of zero memory experiments. So with these axioms, we can define types of probabilities in terms of cause and effect. So in terms of cause and effect, the probability concepts are defined as priori probabilities, conditional probabilities, posteriori probabilities. In the case of priori probabilities and conditional probabilities, the information will be already available in the problem. So it need not be calculated. And what we study in the priori probabilities and conditional probability is the probability of causes. But in the case of posteriori probabilities, it is also called the inverse probability. For a particular effect which has happened, we are going to study the probability of the causes. So the probability is to be calculated for a particular effect. So this is called as posteriori probability. So in order to study the posteriori probabilities, we have to define the theorem of total probability first. So what is theorem of total probability? If B1, B2, etc. Bn, B1, B2, etc. Bn be a set of exhaustive and mutually exclusive events. And if A is any event which is caused by all these events, then what is the probability of that event A? We have taken B1, B2, etc. Bn as set of exhaustive and they are mutually exclusive events. And A is the event caused by all these events B1, B2, etc. Bn. Then P of A is equal to P of B1 into P of A with the condition that it has happened due to B1 plus P of B2 into the probability of happening of an event A due to B2. Like that, from each and every n events, we will be calculating the probabilities associated with this A, which is given by summation over I P of Bi into P of A given Bi. For example, if a company has got n machines, B1, B2, etc., Bn, and each machine is producing some units of the product, and A is an item which has been identified from these n machines, and it is found to be defective. And we are going to study what is the chance that item has been produced by any one of these machines. So an effect has happened. What is the probability that it has been from any one of these causes? Finding the probability for each and every machine to bring out the defective item. In such a case, we will find that probability of B1 into probability of A with the condition that it is from B1. Like that, or it could have been from the machine 2. So P of B2 and the defective item is from B2, or it is from the machine B3 and then probability that it is a defective item. Like that, we add the individual probabilities to get the total probability. And this is called as the theorem of total probability. So this concept is very useful in successful operation of a cross-linked system. Now let us see what is Bayes' theorem concept. If B1, B2, etc., Bn be a set of exhaustive and mutually exclusive events, and if A is any event caused by this B1, B2, Bn, then P of Bi given A is equal to P of Bi into P of A given Bi divided by the total probability. So Bayes' theorem will calculate the posteriori probabilities in terms of priori probabilities and conditional probabilities. So if effect is known, what could have been the probable cause behind it? So this is a very important concept and interesting concept to know what could be the probable cause for an effect which has happened. So in this lecture, we have seen what is an event, the relationship among events, axioms of probability, and then what is Bayes' theorem. Thank you.